So, Lecture 2. A unique solution exists. Recall from last time, first of all, that we're trying to solve this differential equation, right? Time derivatives of y on the left-hand side, time derivatives of the input u on the output side, but we're going to often just call all of the right-hand side the forcing function, f. The left-hand side are time derivatives of y, which, as we've mentioned before, are the outputs. So, a unique solution to this equation exists. We're not yet sure, so this is the lecture as a unique solution exists. It begins. We're not yet sure if a solution even exists for equation 1,1, the equation we just looked back to, and if it does, if it is a unique solution, meaning it's the only solution. So we don't know yet. We have the equation. We would like there to exist a solution. We would like that solution to be unique as well, but we haven't yet determined that. We don't know if this is the case or not. So let's talk about existence and uniqueness. Rather than proving the existence and uniqueness of a solution, which is something that you've probably seen in a differential equations course, maybe or maybe not, but you can look them up, these proofs. Instead of proving it, we will instead just consider a theorem that states conditions under which existence and uniqueness do hold. In other words, a unique solution exists, which is great, and we'll explore the conditions for which this is true. Okay, so we have to impose some conditions on the equation 1,1 in order for that to be true. Let the forcing function f be the right-hand side of equation 1,1. So we already saw that, right? We just called the whole right-hand side f. Then the following theorem we're going to look at. I'm not going to prove, but it can be proved. So, theorem 2.1. Existence and uniqueness. A solution y of equation 1,1 exists and is unique for all time greater than or equal to some initial time t0, if and only if both the following are specified. 1, n initial conditions, where n is the order of the differential equation. So if you have the highest derivative as a 5, which, heaven forbid, we have to solve that one by hand, right? But it's doable. So you would need 5 initial conditions for a 5th order differential equation. So we need n initial conditions for an nth order differential equation, and we need a continuous forcing function f of t for all time greater than or equal to the initial time t0. So those are our conditions. Make the lighting a little bit better. Pretty harsh. I don't know if that's any better. Natural light, artificial light. Okay, so assuming this theorem can be proved, and it can, so I gave you guys a reference. It's actually pretty nice on the web, so you can look it up. We need only the initial conditions and the forcing function to guarantee ourselves there's a unique solution. Let's think about what this means in terms of the dynamics of a system. In a sense, if we know its initial state and the input or forcing, how it will behave for the rest of time is determined. When I say in a sense, pardon Niles, in a sense, I mean that insofar as the system is well described by the differential equation we wrote, 1,1. So it might be nonlinear, for instance, but insofar as it is, it will follow that. The determinist implications of this must be understood to be approximate and limited in scope. I don't want to be responsible for creating a bunch of determinists. Hey Niles, come here, buddy. Come on. Oh, hey, bud. Do you want to come say hi? He thinks that I exist just to serve him, which I guess is true. But anyways, so good. Anyways, that's like a philosophical reference. I encourage you to look it up. Note, however, that given initial conditions and forcing, we only know that a unique solution exists, not what that solution is or how to find it. So, great, we know that that a unique solution exists, but we don't know what the solution is or how to find it. That's going to be most of the rest of this primer course, is the what, how to find that solution, how to find that solution. Okay, outlining a solution technique. It turns out that, given a forcing function and no initial conditions, several potential solutions can satisfy the ODE, equation 1-1. Conversely, given certain initial conditions and no forcing function, several potential solutions can satisfy the ODE. So what I'm saying here is, given 1 but not 2, or given 2 but not 1, if you're given one or the other, several solutions exist. So in order to overcome that, we need both. So like the theorem states, you need both of them. It is only when both initial conditions and forcing function are given that a unique solution exists. It can be shown that the general solution YG, which is typically what we denote the general solution to be, also called the total solution, actually a family of solutions with unknown constants, to equation 1-1. So the general solution to equation 1-1 is equal to the sum of two solutions that are often relatively easy to obtain. The first is called the homogeneous solution YH, another family of solutions, this time to equation 1-1 with the forcing function set equal to 0. So this is the sort of key of the homogeneous solution. We set forcing function equal to 0, and we solve it. That's the homogeneous solution. But we'll expand on that in the next lecture on homogeneous solutions. The particular solution YP, which satisfies equation 1-1, sans initial conditions, so without initial conditions. So we take those two and we sum them up. So equation 2-2 just says YG, the general solution, is equal to YH, the homogeneous solution, plus YP, the particular solution. So that is where we're headed. So if we get the homogeneous solution and the particular solution and sum them up. I'm obviously not proving this to be true, but that's not what this is about. This is about showing you how to do it and not necessarily why it works. So apologies for people who are coming here to learn why the general solution is a solution. Why, if you add the homogeneous and particular solutions together, that you get a unique solution. Well, once you apply the initial conditions. Now, if I wanted to mention that the homogeneous solution, before we go on, I'll mention this in the next lecture, but it is also called the complementary solution. So complementary solution. So for those of you who had that terminology in your differential equations course, same thing, exactly what we're talking about there. So I don't think there's really an alternative for the particular solution. I think that's what pretty much everybody calls it. So methods for deriving homogeneous and particular solutions are the topics of the next two lectures, 3 and 4. The general solution is still a family of solutions that all satisfy equation 1-1 for a given forcing function f. It only becomes the unique solution, which we will call the specific solution, and typically denote simply y or occasionally ys, once the initial conditions are applied to yg. So you get the general solution from summing the homogeneous and particular solutions. Then you apply the initial conditions to get the specific solution. And then you have yourself a unique solution that exists. So existence is important. The diagram of figure 2.1, which I'll turn to in a moment, illustrates this solution technique, with each arrow signifying that the block at its tail is supplied to and precedes the block at its head. lectures proceed with the diagram. So let's take a look here. This is what we start with. We have initial conditions, an ODE, so our equation 1, and a forcing function. So the right-hand side of the ODE, right? So I split it off here just to be a little bit more clear. So what we need first is the homogeneous solution. So you start here and you follow the arrows. The homogeneous solution is first. The particular solution does actually require that you do the homogeneous solution first. It's a little bit subtle why, and we'll talk a little bit about that. So you find the homogeneous solution first, then with the ODE and the forcing function together. So the homogeneous solution, you didn't even need the right-hand side. You didn't even need the forcing function because you're going to set that equal to 0, right? So then we need the particular solution. It requires the ODE and the forcing function. Once you've got those two, homogeneous and particular solutions, the general solution is just the sum. And then if you apply your initial conditions, you can get the specific solution. So that is the sort of algorithm or the flow chart of how we will solve these problems. So, lecture 3 describes how to obtain the homogeneous solution from equation 1 with the forcing function set to 0. Lecture 4 describes how to derive the particular solution, yp, from equation 1 without the initial conditions, the common forcing functions, by a method called undetermined coefficients, which is almost certainly a method that you learned. There's really no C there. Lecture 5 blows your mind by summing the homogeneous and particular solutions to obtain the general solution. I know that one's a tough leap. Lest we be accused of dereliction of our duty to appear smarter than business majors. Notice, I kept it PG there. We just appear. It's our duty to appear smarter. We don't actually have to be smart. Okay. This lecture also applies the initial conditions to the general solution to find constants introduced in the homogeneous solution to fully solve the differential equation, i.e., or in other words, to obtain the specific solution y. So, that's what we're going to do. Before we move on, though, let's do this course connection here. Differential equations. So, all of you hopefully have taken a differential equations course. The technique outlined here is probably quite similar to one described in your differential equations course. Terminology and notation may be different, so it's probably worth correlating this primer with your previous coursework and text. And that is all for this. So, next up is the homogeneous solution.